Welcome everybody to the seminar ABP. Today we have Amol Aggarwal that got his PhD last year with Alexei Borodin in Harvard University. So the shortest career of our speakers here, I think. And he will talk about asymptotics in the stochastic six-vertex model. Amol?
Thank you very much for the introduction and the invitation. So to describe, the main model of this talk will be the Stochastic Six-Vertex model. And to describe it, it might be helpful to first describe what a height function is. So a height function is something like a two-dimensional analog of a walk. So I mean, to more specifically, we'll start with a subgraph, lambda of Z2, and we'll let lambda prime denote its dual or its set of faces. So a height function f is a function for the set of faces of lambda, so from lambda prime to the integers, satisfying that f of u minus f of v is plus or minus 1 whenever u and v are adjacent. So I've shown to the left over here a domain lambda, which is just a square, basically a square grid. And then I've filled in an integer in each face. So that's going to be the height function. And then you can quickly verify for yourself that if I take any two adjacent faces, such as these two, this 4 and this 5, I mean, the height function differs by plus or minus 1. So this is indeed a height function. Okay, so this one-dimensional analog of this is something that you've seen before. By one-dimensional analog, I mean when the domain is one-dimensional. So that's just an interval. So a one-dimensional analog of a height function is just going to be a walk, which is a function f from an interval to the integer, such that the height function goes up or down by 1 every time I move to the left or to the right. So section to the right over here is a walk. I mean, as you can see, it goes up or down by 1 every time I progress to the right. And since this is, a probability submodel, what we'll be interested in understanding is how these objects behave when they're sampled at random. Okay, so what sort of the asymptotic features of these models when I sample them at random? For this model on the right here, we basically know everything about it. It converges to Brownian motion. This model to the left over here, when I have two dimensions, but I'll be basically describing as a two-dimensional ways, our Markovian way of sampling this, two-dimensional height function. And what we'll be interested in understanding is how this height function, this sort of Markovianly sampled height function behaves. Okay, so to do that, it will be helpful to come up with a more diagrammatic description of these height functions, which will eventually lead to the six-vertex model. So so let's fix a vertex just to see what's going on. Let's fix a vertex and look at the four faces surrounding it. By just shifting the height function up or down by a little bit, I can always assume, say that maybe this is just setting notation just to fix the setup, that the height function in the bottom left face adjacent to the vertex h. So in each of these, 6 configurations, you see that. And then look at the height function at the remaining 3 faces surrounding the vertex. Now, due to the fact that the height function can only go up or down by 1 every time I pass through an edge, you can quickly convince yourself that there are only 6 possible local configurations of the height function surrounding a vertex. For example, at this top left, this guy over here, we see that the height function is h at the bottom left, as we always fixed. It's h minus 1 on the top left, h at the top right, and h plus 1 at the bottom right. Okay, and likewise here we see h at the bottom left, h minus 1 at the top left, h minus 2 at the top right, and h minus 1 at the bottom right. Okay, there are 4 other possibilities which are listed over here. So these are 6 possible local configurations of the height functions. And what we'll start doing is we'll decorate these local configurations by arrows according to local rules. And these local rules just depend on the gradient of the height function as I pass from face to face. So how this works is that if I start from a face and go to the left, so I take 2 adjacent faces, I go from the left to the right. If the height function drops by 1, I put an arrow, a vertical arrow along the edge separating these 2 faces. And if it increases by 1, I put nothing there. And now if I go from top to bottom, if the height function increases by 1, I put nothing there. And if it drops by 1 from top to bottom, I put a horizontal arrow at the edge separating the 2 faces, shown over here. So decorating. So if I decorate these local configurations, I got something that looks like this. Just to check to make sure that I haven't lied to you. We can take this vertical arrow over. We can take this face over here. So as you can see, when I go from h minus 1 to h, I've increased the height function from top to bottom. And if I look at my sort of little cheat sheet over here, this tells me that I don't put an arrow, and I didn't. Okay, now if I go from say h to h minus 1 from left to right, this is telling me this my cheat sheet again tells me that I do put an arrow. And so I did put an arrow here. Okay, and you can convince yourself that, just run around the face, and you can convince yourself that hopefully I didn't mess up and I put the arrows in properly. Okay. So I've just added I've added arrows. I've decorated these sort of local configurations by arrows that just depend on the local gradient of the height function. And the moment I tell you what the arrows are, you can, and I tell you, say, I fix the shift, I tell you that H is the guy at the bottom left face, you can reverse engineer these local rules, and you can fill in the values of the height function everywhere around the face. Okay, so I mean, arrow configurations are in direct correspondence with these local height functions, these local height configurations, and therefore what I'll often do is I'll just erase the height function. Okay, I'll only think about the arrow configurations. I can go back and forth between the two. Now, so this produces 6 possible arrow configurations, which are, I mean, just in direct bijection with the 6 possible local configurations of the height function. And they satisfy, you can quickly see actually that they satisfy what was known as spin conservation, which is that the same number of arrows go into the vertex as leave the vertex. For example, here, no arrows come in and no arrows come out. 2 come in and 2 come out at this A2 vertex. And at the remaining 4 vertices, 1 come in, one enter and 1 exits. Okay. And this is a simple reflection of the fact that when I cycle around a vertex, when I loop around all 4 faces, I get back to the same height function. So that's, I mean, if you sort of think about these local rules for a minute, you'll realize that this is exactly the statement that in terms of the arrows that you have the spin conservation, the same number of arrows enter as exit. Okay, so just to sort of put things together so far, what we have is some height function on some domain. Here again, I'm taking a square domain. You can add in arrows according to the local sort of gradient rules in the previous slide, and you'll get something that looks like this. And I can erase the height function. I will get just an assignment of arrows to each vertex satisfying the spin conservation. And a 6-vertex ensemble, by definition, I'll just use this terminology from now on, as an assignment of an arrow configuration to each vertex of my domain. And as I mentioned before, there's a bijection between 6-vertex ensembles and arrow configuration and these height functions up to a global shift of the height function. So if I fix my height function to be 0 at the bottom left face of the square, and I give myself the arrow configuration, I can just reverse. I mean, like sort of use those rules, these sorts of rules here on the previous slide to fill in what the height function should be everywhere else, and I will get this. Okay, so there's a bijection between the two. Okay, so what will be somewhat relevant in this talk is the notion of boundary data. So from the perspective of the 6-vertex model, these are the locations where the arrows enter and exit the domain. So on the left, so as you can see that in the specific example I've shown here, they enter the domain along the left boundary and exit along the top boundary, and there's no action happening on the bottom and on the right. Okay, so so that's in terms of the 6-vertex ensemble. In terms of the height function, boundary data is sort of what you might imagine in principle. It's that the height function, the boundary data is by definition the values of the height function along the boundary. So the height function would be sort of 0 through 7 along this boundary, 7 through going down, 7 through 0 along this boundary, 0 through 7 here, and 7 through 0 here. So I'm going up, down again, if I sort of cycle around the boundary. So these are again just the ways of how to describe boundary data for my model. Okay, and one more point I want to just mention before proceeding is that these 6-vertex ensembles can be viewed as collections of non-crossing but possibly touching paths. So for example, if you can see my cursor over here, you see one path, sort of just a tiny little path that enters and just immediately exits the domain. The next path kind of zigzags and goes like this, and you have these other paths in the model. And the bottommost path is sort of this one. It goes straight 3 times, it goes up, it goes straight, it goes right, it goes up, it goes right, it goes up, and then it sort of, etc. Right. So these are the paths in the 6-vertex and the 6-vertex ensemble. And I will always view them as possibly touching. Like for example, you see that the paths touch, these 2 paths touch over here, but they don't cross each other. Okay, so all of this so far has been purely deterministic. I haven't put any probability in the game yet, and this is what I want to do next. Okay, so I'm going to define a probability measure on the set of 6-vertex ensembles, and this is going to be known as the 6-vertex model. Okay, so let's fix some 6-vertex ensemble. We'll call it E on some domain lambda. We'll imagine this domain is finite, some finite domain lambda. And we'll fix some real numbers, which will eventually be weights, A1, A2, B1, B2, C1, and C2, which are all non-negative. and we'll assign to each arrow configuration a vertex weight. So the empty arrow configuration that has no arrows coming in and no arrows coming out has weight A1. The sort of full configuration that has 2 arrows coming in and 2 arrows going out has weight A2. The sort of double vertical has weight B1. The double horizontal has weight B2, and these 2 corner vertices have weight C1 and C2. Okay, so I've assigned weights to each of the 6 possible arrow configurations, and I'll assign now a weight to the whole 6 vertex model, the whole 6 vertex ensemble, in the sort of classical way we do in statistical mechanics, which is basically I take A1 to the number of A1 vertices times A2 to the number of A2 vertices, etc. So I've shown an example over here where I've taken a 6 vertex ensemble on some, on some 4 by 6 grid, okay? And I'm claiming that its weight is A1 to the 8, A2 to the 7, B1 cubed, B2, C1, C2 to the 4. Okay, and you can, just to convince yourselves maybe the first 2 terms, you can quickly see that there are exactly 8 A1 vertices, 8 empty vertices, and 2 of them are here and 6 of them are here. There are 7 A2 vertices, and 6 of them are sort of forming this triangle, and there's 1 more, etc. Okay, so that's the weight of this 6 vertex ensemble. Okay, and we can define a probability measure by saying that the probability of a given ensemble is proportional to its weight. Namely, the probability of seeing ensemble E is Z inverse times W of E, where the partition function Z is defined to normalize this probability measure to sum to 1. Okay, and as I said before, you can view this as sort of a prototype model for a Markovian growth of a random surface. Okay. So now I want to make this. This growth will not. This will be a Markovian. This will be a prototype model for a discrete random surface. But what I want to do next is describe a way of growing the surface in a Markovian fashion. I mean, as I just did before, this is sort of an equilibrium model, something like an Ising type model or something like that, where I've just I've given you a weight for each face, but I want to actually describe a way of growing this face in a Markovian fashion, much like you grow a random walk you grow a random walk. I want to describe a way of growing a random surface. So to do that, we will specialize these weights in a certain way. Okay, and that will be this was suggested by Guan Schwan back in around 30 years ago, which is to set A1 and A2 equal to 1, so the empty and the full vertices have weight both equal to 1, and I will let B1 and B2 be arbitrary, but between 0 and 1, and we'll let C1, so this is this corner vertex equal to 1 minus B1, and C2 equal to 1 minus B2. Okay, and the reason behind this this choice of weights is that it satisfies the following so-called stochasticity property, which is that if I fix which arrows enter the vertex, and I look at all possible vertices that have this given incoming arrows, then the sum of their weights is equal to 1. Okay, so let me just check this here in these examples. So if I imagine that no arrows come in, there's only one vertex of that type, which is the empty one. No arrows had better go out, and that has weight 1. Likewise, if 2 arrows come in, then there's again only one possibility that both arrows have to go out. And again, this is the full vertex, which has weight 1. Okay, now the things get a little bit more interesting when I have 1 arrow coming in vertically, say, and no arrows coming in horizontally. So now there are 2 arrows, there are 2 configurations of that type, the 3rd and the 5th, right? Okay, and as you can see, the sum of the weights is 1. I mean, the double vertical has weight B1, and the sort of one where this arrow turns to the right has weight 1 minus B1. And likewise, if I have 1 horizontal arrow coming in and no vertical arrow coming in, there are 2 possibilities shown by the 4th and the 6th, and their sum of weights is again equal to 1. So the stochasticity property enables you to sample this vertex model, this 6 vertex model, locally, basically from vertex to vertex, or eventually from row to row. Okay, so I'll try to explain that in this sort of little picture over here on the bottom. Okay, so I'm going to start at the bottom right, where I have this vertex where hopefully you can see my cursor, a vertical arrow is coming in. Okay, so I go to my set of 6 vertices, and I see there are 2 configurations. There are 2 possibilities for what this arrow might do. It can go straight through, or it can pass to the right. Okay, so flip a coin, and with probability B1 as shown over here, it will go straight up, and with probability 1 minus B1 as shown in this fifth configuration, it will go to the right. Okay, so I flip my coin. Let's say it goes straight to the right with probability 1 minus B1. Okay, so then I go to the next vertex, which is the one adjacent to it to the right, and I see now that it has 2 arrows coming in, right? Okay, and I look back at my sort of 6 possible configurations here, and I see that there's only one possibility. It's forced. There's only one situation. If 2 arrows come in, they better both go out. Okay, as shown in this vertex over here. So deterministically, these 2 arrows will pass straight. Will go out. Okay, now I go to the next vertex, which is again to the right. I keep on going to the right each time. So I have a horizontal arrow coming in, and again I see two possibilities given by the fourth and the sixth local configurations over here. So again, I'm going to flip my coin. With probability B2, it's going to go straight through. With probability 1 minus B2, it's going to go up. Okay, and let's say it goes up, and then I keep going, right? I mean, I keep flipping my coins and seeing what happens, and I do that. Okay, so now I've finished sort of the row, and I've seen which arrows I entered this row, and now I've sort of sampled in the sort of local, vertex to vertex fashion. I've sort of sampled how the arrows exit the row. Okay, and then I can just iterate this fashion. I can keep going up and up, and I will eventually sample some sort of six vertex model in the whole domain. This six vertex model in the whole domain. Okay, so that's what I mean when I say it's sort of a Markovian growth of the six vertex model, or equivalently, if I sort of fill in the height function everywhere else, which I didn't do and often I won't do, you can view this as an evolution of this random surface, as a way of constructing in a Markovian fashion this random surface. Okay, so another interpretation, which is perhaps closer to this audience, is that you can view this as an interacting particle system. Okay, and you can view this as an interacting particle system by viewing the y-axis as indexing time, and the particles along any row, so the vertical arrows as along any row as particles. So for example, over here, I imagine that at my initial time, I have a particle, let's say sites 1, 2, 4, there's wherever the arrows are. So 1, 2, 4, 7, and 9. And then at the first time step, the first particle jumps to the right by 1. The second particle also jumps to the right by 1. The third particle over here jumped to the right by 2, as you can see. The fourth particle stayed put, and the fifth particle jumped to the right by 1. Okay, and likewise, you can, so you can sort of view time as going up as the y-axis, and particles as these vertical arrows. Okay. So again, I want to make a closer analogy to the stochastic six-vertex model and interacting particle systems that you know well. And in fact, there's a very direct correspondence between the stochastic six-vertex model and the ASEP. So to sort of warm up, I mean, it's a fairly simple correspondence, but it will help to just sort of do a very, very simple warm up, which is this just to set B1 and B2 equal to 0. Okay, so in this case, the weights of having the arrow go straight through either vertically or horizontally are both equal to 0, and all of the other weights are equal to 1. So this totally sort of freezes the model. There's no randomness anymore. All of my coins are completely rigged, and they're either going to land, and they're only going to, whenever I flip a coin, it's only going to land on these two corner vertices. So paths deterministically sort of zigzag. They always sort of go upright, 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 upright. Okay, and what that means is that these paths move diagonally, so they're constant along a diagonal reference frame. So another way of saying that, maybe a more precise way of saying that, is I again view the y-axis as time, and I'll say that a vertical arrow exiting at a site xt is the same as saying that there's a particle at time t and site x minus t. So time t is again reflective of the fact that I'm viewing the y-coordinate as time, and site x minus t just means that I'm looking at this diagonal reference frame. So I'm sort of, so I have this diagonal reference frame going on. And under this interpretation, the particle configuration is just constant time, just again, due to the fact that these paths deterministically zigzag. Under this diagonal reference frame, the particles are just not moving in time. So that's not very interesting. So what I'll do next is I'll turn on B1 and B2, but very slightly. Okay, so I'll set B1 equal to some epsilon R, epsilon L, and I'll set B2 equal to epsilon R, where epsilon is some very small number and L and R are some, say, real numbers, positive real numbers. Okay. So now what will happen is that since epsilon is fairly small, not much has changed from what I had before. Paths will usually go diagonally, but every once in a while, every very rare once in a while, the paths will take one extra step to the left. These paths will take one extra step to the left, which corresponds to a double vertical, or one extra step to the right, which will correspond to a double horizontal. Okay, so again, if I view my particle system, if I sort of view a vertical arrow as exiting from site xt as a particle at site x minus t, a particle at site x minus t at time t, these particles will usually stay fixed, but every once in a while they'll jump. Every once in a while they'll jump to one space to the left or one space to the right. Okay, and again, one space to the left corresponded to a path sort of staying put, like sort of a path going straight up. Again, because in this diagonal reference frame, if a path goes straight up, it actually means that the associated particle jumped to the left by 1. And likewise, this sort of double horizontal means that the particle jumps one space to the right. So immediately you see sort of an ASEP going on here, right? If I let epsilon tend to 0 and I scale time by 1 over epsilon, then these sorts of these Bernoulli type probability and these coin flips will converge to pulse endpoint processes. I mean, these sort of Poisson processes, and you'll see you'll exactly get the ASAP. I mean, particles jump to the right or jump to the left with rates R and L respectively. Okay, so this is a direct way of sort of getting the ASAP from the stochastic six-vertex model. Okay, so I've so far I've described to you this stochastic model, which can be viewed as an interacting particle system, and then we want to play all of the same games that we play in this context, which are understanding the structure. I mean, the large scale structure of these interacting particles, or this stochastic six-vertex model. So I'll start by stating a theorem here, which is to that effect. So we'll consider the stochastic six-vertex model with height function h of n. So this height function, I mean, again, there's a bijection between height functions in these stochastic six vertex ensembles. So I'll often codify. I mean, I will often sort of quantify this height ensemble through the height function, much like you would often in interacting particle systems. You'd quantify the particle configurations through the current, say. So we have the stochastic six-vertex model with some height function h of n. So n will be some large scaling parameter on the upper half plane. So z cross z bigger than 0. So this z is the x-axis, and this big z bigger than 0 is the upper half plane. Okay, and we'll have some boundary data, which you can view as initial data, which tells you where the particles, the arrows enter the x-axis through the x-axis. They're determined by, as I mentioned before, they're determined by the restriction of the height function to the x-axis. So the restriction of the height function to the boundary. So by h of x0, where x is ranging across the full x-axis, and we'll fix some Lipschitz height function. We'll fix some Lipschitz function psi, which is kind of giving you the initial data. So psi is some Lipschitz function from -1, 1 to r, and we'll assume that this height function, again, the initial data sort of converging to it in the sense that 1 over n times h of nx0 is converging to psi of x on this interval as n tends to infinity. Okay, now I'll have my six vertex parameters, b1 and b2, and we'll define this rational function phi of z, which is kind of like the flux function for this, which will be the flux function for this stochastic six vertex model. It's defined explicitly, so phi of z, it has z as an argument, and it's some rational function in z. As you can see, it has this kappa involved in it, and kappa is explicit in terms of b1 and b2. Okay, so the theorem is the following. Okay, so I've taken my six vertex, the stochastic six vertex model with this initial data h of n, which converges to psi. And the statement is that if I scale in the linearly, if I take the side function at 1 over n times h of nx xn yn, it will converge to a deterministic limit given by this sort of math frac h of xy. And this deterministic limit is given by the entropy solution to this Burger's type PDE. So I mean, so it's partial y of h is equal to this phi of minus partial x of h, with the initial data being given by h of x0 is given by psi of x, as you would expect the initial data to be given by. Okay, so this theorem applies in other domains such as the cylinder or the quadrant. I mean, the domain is not so important for the statement of this theorem. Okay, so this is a theorem on how the sort of a hydrodynamic type limit shape for the height function of this stochastic six vertex model. So let me just make a few comments. I've just repeated the theorem up here. So this was predicted early in the physics literature by Guan Spon back when they introduced the model in 1992. And their heuristic, I mean, their prediction was based on a hydrodynamic limit for the underlying interacting particle system that I had described before. Now, such limits, such sort of hydrodynamic limits are well developed. There's a framework, many frameworks by this point that are well developed in the context of continuous time exclusion processes. Now, the somewhat tricky point behind the stochastic six-vertex model is that it's discrete time, which is maybe not so bad, but it's sequential, which is much more painful in the sense that, going back to this sort of picture I had here, it really did matter that I started from the left and went to the right. I mean, it was very important that I started at this vertex here and started updating to the right. I mean, so I had to go from left to right when updating this particle system. This makes the generator of the model somewhat painful to work with. So, I mean, various of these frameworks somewhat break to a certain extent when trying to prove these hydrodynamic limit theorems for the stochastic six-vertex model. Okay, another comment is that this result was predicted in a somewhat different way by Reshetik and Sridhar back a few years ago, and their heuristic was based on their prediction was based on a heuristic variational principle. So if you look at other models of height functions, such as dimers, there's a variational principle that governs the limit shape, and they tried to produce a similar sort of heuristic underlying this theorem. that variational principle is somewhat different, which I mean different from the well-developed ones, which is why their prediction was somewhat heuristic and not quite proven. Okay. So I should say a special case of this theorem in the case of Riemann profiles, which are corresponding to when the derivative of psi, which is kind of the density, is piecewise constant. So in particular, it's rho to the left of 0 instead of lambda to the right of 0. When lambda is bigger than rho, which sort of corresponds to a rarefaction fan, was proven basically in works of Borden, Corwin, Gorin in 2014, and then by myself and Borden in 2016. Okay, so I've given so far a description of the behavior of the hydrodynamic limit, and what I want to talk next are local statistics of this height function of the stochastic six-vertex model. So basically, the question I want to understand is what is the local small-scale sort of behavior of the stochastic six-vertex model in fairly large domains. So once again, we'll consider some stochastic six-vertex model on say an upper half plane or a quadrant. I mean, with some boundary data. Okay, and we'll fix some vertex in the domain, and we'll consider some order 1 neighborhood of it. So as the picture I have over here, I guess my picture is actually on the quadrant. I have some stochastic six-vertex model, and I fix some domain. I fix some vertex V, which is inside this tiny little box over here, and I'm considering some domain, which is say some 10 by 10 domain or something like that. Okay, and I zoom in and I ask myself, okay, so then I have some random six-vertex ensemble on this domain, on this big domain, and so that will restrict to some random six-vertex ensemble on this little of 1 neighborhood. And the basic local statistics question is, what is the law of this random ensemble? So, I mean, this is kind of, I mean, you can kind of view this as an analog of convergence to local equilibrium for hydrodynamic, for interacting particle systems. And if you sort of believe that analogy, what you would expect is that this will converge to a stationary state with the appropriate density. Okay, so I want to now take a moment to describe what these stationary states look like, and they will sort of be like product measures. To describe it more properly, it will help to first describe what these stationary states look like on the quadrant, and then I will take this quadrant to sort of exhaust the full plane. Okay, so we'll consider again the stochastic six-vertex ensemble of the quadrant, say z bigger than 0 squared. Okay, and I'll define double-sided Bernoulli initial data to be double-sided Bernoulli boundary data to be a specific way of boundary data for the six-vertex model on this quadrant. And what that's defined by doing is I set sites on the y-axis to be independently entrance sites for arrows with probability t plus 1/2. So, I mean, you might want me to do it with probability t, but it's actually helpful to do it with probability t plus 1/2. I mean, just, yeah, okay. And then sites on the x-axis to be entrance sites for arrows with probability s plus 1/2. So t and s are ranging between -1 and 1. Okay, so these probabilities range between 0 and 1. Okay, so it might look something like this. So, I mean, I have arrows entering randomly along the y-axis and arrows entering along the x-axis randomly. Everything is independent. Okay, so this is sort of just a product measure. Now, in the special case when t is equal to this phi of s, and this phi is this rational function that I had written down before that involved this kappa, then this double-sided Bernoulli has a certain stationarity property. We call it stationary in the sense that if I restrict to subquadrants, then you again have this sort of double-sided Bernoulli property. So I tried to draw that in this picture to the right over here. So as you can see, I have this quadrant over here, and I have these arrows entering through the y-axis with probability phi of s plus 1/2, and through the x-axis with probability s plus 1/2. And then if I take some like subquadrant, if I cut out a little quadrant over here, like that has the two axes intersecting at some vertex xy, then again, you'll see that the arrows enter independently. Everything's independent again. The arrows enter along the y-axis with probability 5s plus 1/2, and to the x-axis with probability s plus 1/2. Okay, so you can kind of view this as an analog of the Burke property for TASUP or queuing systems, and this will actually be false if I don't take t to be 5s. So it's very important that you take t to exactly be 5s for this to work out. So the proof of this is maybe not is not so hard. I mean, once I tell you it's true, it's not so hard to verify it. I mean, this phenomenon also doesn't only hold for quadrants; it holds for sorts of I guess they're called space-like paths, where the paths go down to the right. So you can prove this theorem by sort of just doing a local check by sort of by kind of an inductive argument. Okay. So now I only define this thing on the quadrant. I want to define this thing on the whole plane. But once I tell you the stationarity property, it's somewhat straightforward to do that. You just kind of drag the quadrant back to -infinity. So more specifically, what I'll do is I'll define just by definition mu 0 of s is the stochastic six-vertex model on the quadrant that has this Bernoulli initial data with 5s along the y-axis and s along the x-axis. Okay, now mu n of s is going to be the shift of mu of s down by minus nn. So I'm just dragging this thing down into the left by n in both directions, and this is going to be this mu n of s. Okay, now the stationary condition tells me that mu m of s is the restriction of mu n of s to whenever I have like m is less than n, then mu m of s is going to be the restriction of mu n of s to the subquadrant, which basically tells me that that this limit, as I drag this quadrant down to infinity, this mu of st, where t is 5s, is well defined. So I can take this n to infinity and I'll get some well-defined measures, six vertex measure on the full plane. Okay, so this will sample what in the sort of the statistical physics jargon for what we call such a measure is going to be a pure state of slope s of phi of s, or st, for the stochastic six-vertex model. I mean, so again, this is just some terminology which I won't use too much, but I mean, in case you're curious, the word pure state means a translation-invariant extremal Gibbs measure, and the slope. The reason we say it has slope st is that if I look at the associated height function, it's going to be linear. Again, I mean, you sort of have the stationarity of this translation invariance, and therefore you expect the height function to be linear. And the slope will literally be st. I mean, in the sense that, or maybe minus st, in the sense that, h of 0, 0 minus h of 1, 1 is going to be s, and h of 0, 1 minus h of 0, 0 is going to be t. I mean, so yeah. So in that sense, this sort of height function literally has this slope st. Okay, so going back to the local statistics, I want to now state a theorem concerning local statistics of the stochastic six-vertex model. So we'll consider the stochastic six-vertex model E, and again, let's say on the upper half plane. Again, the domain is not so important, really. And we'll have some initial data, again, that converges to the psi of s, this psi of x as I had before, for some Lipschitz function psi. Okay, so this Lipschitz function psi can be whatever you want. Okay, it doesn't have to. This is actually going to be sort of a creation of local equilibrium statement instead of a conservation one. So psi of s doesn't have to have any sort of local equilibrium qualities associated with it. I mean, for all I care, it could be completely deterministic. Okay, so again, so I have this height function initial data is conversion to the psi of s. I'll have the entropy solution as I did before to this limiting PDE. And I'll let xy, so you view it as a macroscopic point in the upper half plane, such that it's a continuity point for the gradient of the limit shape. Okay, so the limit shape is some h of xy, and I'll say that the gradient of h of xy is continuous at xy, and I'll set its value to be minus st. Okay, okay. So now observe now that because h satisfies this PDE, remember that basically from the previous slide, t was morally speaking the y derivative of h. So the left side of this PDE is t at xy, and the right side at the partial x of h was equal to s, right? So basically what this is telling me is that if I know that, since I know that h satisfies this PDE, you better have that t is equal to 5s, again, just by plugging in the values, I mean, just plugging in xy, evaluating this PDE at xy, you'll get that t is equal to 5s. Okay, so so now the theorem then is that as n tends to infinity, the local statistics of this, random six vertex ensemble around the vertex nx and y is converging to this sort of local equilibrium measure, this pure state mu of st that I had before. Okay, so you can view this as a convergence to the local equilibrium, or maybe even a creation of local equilibrium result for the underlying discrete time sequential interacting particle system. So in the context of continuous time interacting particle systems such as the ASAP, this is due to Bahadorn and Mountford in 2006. Again, just to draw the analogy with interacting particle systems. Okay, now this is somewhat of a digression, but I want to describe. So I've already mentioned to you that this Bernoulli measure for I mean this sort of mu st measure that I had over here was stationary for the stochastic six-vertex ensemble. What I want to describe sort of another way of seeing that, which is maybe overkill because, as I said, the proof is not so hard. But it's somewhat enlightening description of why this is true from a rather different and more algebraic perspective using commutation relations. I'll go somewhat faster because maybe this is not the main focus of this talk, but I want to. It's somewhat pretty in my opinion, so I want to quickly describe it. So. So I see a comment here, which is that this looks very much like Boozman. So what exactly looks like a Boozman function?
Pode falar, Leandro.
Okay, I just it looks like convergence to Guzman functions of less passage preparation times. What you just showed.
Yes. That would be if you have the perspective of right. So this convergence to local equilibrium result. If you look at sort of the last passage analog of this thing. I mean, again, the models are somewhat of different natures, but yes, there is a fairly close analogy between this sort of local equilibrium statement and a convergence of Guzman functions. You're exactly correct. Yeah. Okay. So I want to take a moment now to describe a way of sort of seeing the stationarity through a family of commutation relations. And these commutation relations do eventually play a big role behind the algebraic theory behind the stochastic six-vertex model. So again, I'm going to do something that's kind of overkill. I'm going to try to show that the Bernoulli measure on a line is stationary for the stochastic six-vertex model. Okay, but this will have, I mean, yeah, okay. So let me just do it. Let me just sketch it very quickly. Okay, so I'm going to define this vector space V, which is V1 tensor V2. Let me go ahead and do as you suggest. So I will turn off my camera. Okay, thank you for that suggestion. Okay. So again, we interpret the basis element states of the six-vertex model. So whenever I have an E1, I have a vertical arrow. Whenever I have E0, I have an arrow. Okay. So I'll define this transfer matrix T1 of B1 and B2. So it depends on the parameters B1 and B2 of this stochastic six-vertex model. It's a map from B to V. Transition is given by, if I have two sigma and omega, it's given by the value of T1. If I sandwich it between sigma and omega, it's given by simply the partition function of the probability from going from omega to sigma. Okay, under this stochastic six-vertex way here. Okay, I often set, because I will often use this notation later on, I will often set B1 over B2 equal to Q, which is just some number. I mean, it's the ratio of B1 and B2. Okay, so if I have, so now what I'm going to do is I'm going to define a different operator. So I've defined one operator, which is this transfer matrix T1. I'm going to define a different operator, which will satisfy certain commutation relations with T. And these commutation relations will exactly give you, it will exactly eventually correspond to the stationarity condition. So we'll fix some parameter rho, which you should use kind of the density for a Bernoulli state. And we'll define this operator x of rho, which acts from V to V again. It's an endomorphism of this vector space V. And it's given by a transition probability again. So this sort of sandwich, if I sandwich x of rho between omega and sigma, it's given by the transition probability from omega to sigma under these. Okay. So let me quickly describe what I mean here. So these weights are no longer going to be the stochastic six-vertex weights. These are given by somewhat different weights. And so what you should think of as the following. Okay, so you have like sort of infinitely many arrows, a bundle of infinitely many arrows is entering through the left vertex. Okay, and every once in a while, it's sort of depositing arrows, collecting arrows as it moves along and sort of depositing them out over here. Okay, so the rules for depositing them, it's depositing them according to a sort of stochastic procedure, and the rules of the depositing them are given by sort of the following chart. So what you should view as sort of this arrows is infinite. It has this sort of vertical line, this horizontal line consists of infinitely many arrows. Did the internet break again?
No, we can still hear you.
We can hear the sound is not that good as before, but
you can still see me. Okay, I thought my internet broke. Oh, okay. So we're still good. Okay, good. Okay, sorry. I got worried again. Okay, just let me know if something goes wrong. Okay, okay, right. So the weights for how the arrows deposit themselves along how the arrows exit are given according to this chart over here.
Screen.
So I imagine
Amol, we lost your screen.
Oh, my screen is lost. I see. Okay. So let me share again. Yeah, sorry for all these technical difficulties. Okay, so let's keep going then. Okay, so I'm going to keep track of the number of, so this D here is sort of keeping track of the number of arrows that are lost in this procedure. So it's the number of arrows. I mean, so as I said before, the sort of infinite thick arrow gains and it loses arrows as it sort of proceeds along, from point to point along this horizontal edge, and it deposits arrows according to certain rules, and this D here is tracking the number of arrows that it's lost under this procedure. Okay, so if I've lost D arrows, then if I have no arrow under with probably one row, it does not deposit an arrow, and with probability rho, as I can see in this sort of fourth picture over here, it does deposit an arrow. So actually, this is independent of D. If there's no arrow underneath it, then the action of the sort of thick arrow, depending like whether or not it deposits an arrow, is independent of D. But now, if there is an arrow beneath it, then the sort of thick arrow can either collect the, or it can like sort of have the arrow pass right through it. And this happens with some probability that depends on D. So it's, q to the D times 1 minus rho plus rho, or 1 minus q to the D times 1 minus rho. Okay, so I've defined this thick arrow that kind of collects and deposits arrows as I proceed along. Okay, and it satisfies a certain code. So T1 x of rho is equal to x of rho T1. And the reason for this is sort of, there's sort of a quantum algebraic reason underlying this phenomenon, which is the so-called Yang-Baxter relation, which is the following. Okay, so if I have two numbers B1, so if I have B1 and B prime and B1 and B2 and B1 prime and B2 prime that each have the same ratio of Q, then it's a fact that these two transfer matrices I had in the previous slide, these two sort of stochastic Six-Vertex transfer matrices, T1, B1, B2, they commute. So I'll take that sort of for granted. Another thing I'll take sort of for granted is this notion of so-called fusion, which is that this operator x of rho, it can be viewed as a composition of these T1s, but with different values of B1 and B2. So namely x of rho, you can view it as T1 of some B1, B11, QB11, B12, QB12, etc. So some sort of composition of these original sort of six vertex operators. If I pick my B's correctly and I sort of pick my J correctly, and I have to kind of do some sort of analytic continuation behind it. But the point is that X is really a composition of T1s. So once I know this sort of Yang-Baxter and this fusion, the commutation immediately follows, right? I mean, it's a simple consequence of the fact. I mean, I have this T1 of B1, B2. I can pass it to the right of each of these little each of these T's that are involved in the composition product describing X. So that's how you see the commutation relation from these two properties. Well, I won't describe how to prove these two properties. These are somewhat algebraic notions. These are, Okay, now how to see the stationarity from this? So the basic idea is to simply apply the commutation relation to the vacuum vector, the empty arrow configuration, E0 tensor, E0 tensor, E0, etc. So again, acting on as I mentioned before, if I act on the empty side, then the sort of X rho, this thick arrow, it deposits it with probability 1 minus rho, it doesn't deposit an arrow, and with probability rho, it does deposit an arrow. So as you can see, if I act on this vacuum vector, this X rho is literally producing this rho Bernoulli initial data. Okay, so on the left over here, on the left side of this equation, I've acted by X rho on the empty, and then I've applied T1. So X rho is producing a Bernoulli profile, and T1 is just acting by the Stochastic Six-Vertex model on it. So this is just the action of the Stochastic Six-Vertex model on a Bernoulli. Okay, and the notion, sorry, hello? Did someone ask something?
No, you can continue.
Okay. And the notion that this is stationary is exactly the notion that I get Bernoulli back after doing that. Okay, I should get exactly the same. I should get Bernoulli, the Bernoulli condition again by doing that. Okay, so so let's look at the right side over here. First I've acted by T1, which is only outputting one arrow. Okay, so technically it's outputting an arrow. But if I look very far to the right, so I'm kind of looking in the infinite volume sort of limit. I mean, well into the bulk. I'm not going to see that arrow, and therefore I'm acting basically, if I look very far to the right, I'm acting by this X rho on again an empty profile. So this is again going to produce to me a Bernoulli. So the right side is just basically giving me Bernoulli if I look sort of in the tail into the bulk, and the left side is also giving me the action of T, the stationary stochastic Six-Vertex on the Bernoulli. So this is exactly the stationarity statement that, if I act on the stochastic Six-Vertex by Bernoulli, I get Bernoulli back. So this is giving you basically sort of a way of seeing that this product measure is stationary for the stochastic Six-Vertex model. Okay, so as I mentioned before, this is kind of there are many ways of seeing that, but I mean, maybe something less obvious is that you can do the same whole game for multi-species vertex models. So there are multi-species versions of this stochastic six-vertex model. And if one does this, you'll actually get the same sort of game, exactly the same game. You can define this T1 operator, you can define this X row operator, and what you'll get are stationary measures for the multi-species models, and they will exactly spit out the measures, these sort of these queuing measures that were introduced by Martin back in 2018. So this is sort of a way of deriving these measures of Martin. Okay. So are there any questions so far?
Yes.
Okay. So if not, oh yeah. Yeah.
Let's see.
So I have a question.
Yeah, please, Milton.
Yeah, so these transfer operators that you were mentioning are related somehow to this type of operators that appear in beta ansatz type of computations.
Correct. Yes, that is correct.
Okay.
Yeah, that is the source of these commutation relations. I mean, these commutation relations are I mean, the Young vector is sort of underlying these beta ansatz computations. Yes.
Okay. Okay. Thank you.
Yeah. Okay. Any other questions? Okay, so if not, I want to quickly describe. So Pablo, I'm not sure how much time I have left. I understand if it's not much due to the internet crashes, but I can, if you tell me, I can sort of see how much more I want to go.
Let's say 10 minutes from now. It's okay.
10 minutes. Okay.
Yeah.
Okay. Good. Okay. Good. So what I'll do in the remaining parts of this talk is I'll quickly describe a fluctuation statement where you'll see a kind of KPZ type fluctuation, and then I'll give you a few lines on how to prove the limit shape result, and then I'll stop. Okay. So let's start with these fluctuations. So I'm gonna state the fluctuation for this sort of stationary stochastic six-vertex model. So we'll say again that T is 5s before, and I'm gonna sample this six-vertex ensemble on Z2 on the full plane according to this stationary measure, this mu of st. I'll denote its height function by h as I've always done, and I'll set h of 0, 0 to be 0 just by shifting. Okay. Now again, since this mu of st has the slope st, as I mentioned before, the expectation of h of xy is given by ty minus s of x minus sx. Okay, I mean this is linear, right? So let's subtract that away and try to understand from h and see how this thing fluctuates. So the statement, the theorem back from 5 years ago is that there exists explicit constants omega and d, and they depend on sort of b1, b2, and s, so that the following holds. Okay, so I take my height function h and omega of x. So omega you should view as sort of a characteristic direction, much like in the ASEP, you see the KPZ fluctuations along a certain characteristic direction at stationarity. I look at h of x, omega of x, and I subtract away the expectation. The statement is that this thing will fluctuate on order x to the 1/3. And if I divide out by x to the 1/3, the probability that this is bigger than some z converges to a distribution. And this distribution is known as the Bike-Rains distribution. It's given by a somewhat complicated formula, and I won't write it down, but it's some explicit density function. So the sort of qualitative statement, another way of saying this is that along this characteristic line, y is equal to omega of x. The height fluctuations are anywhere off this line, they'll be able to enter the 1/2 of the Gaussian. So maybe a quick picture is that I have my, I take my stochastic six-vertex model in the quadrant. I have this characteristic line, which is y is equal to omega of x. Along this line, I see the Bike-Rains distribution. Everywhere off of it, I see Gaussian of order x to the 1/2. Okay. So using this theorem, you can also analyze the so-called two-point function. So if I let chi of v denote the indicator function, for a vertical arrow exits from a, say a particle exits at some site V in a quadrant, I can define this S of UV, this 2-point function of the space-time covariance, given by the covariance of chi of U and chi of V. So now the statement is that if U minus V is parallel to this characteristic line, to this, this line of slope omega, then S of UV has it decays like a power law with power t minus with power law 2/3. So it's like U minus V to the 2/3. And everywhere off, if U minus V is anywhere not parallel to the characteristic line, and this S of UV will decay exponentially. Okay, so again, you kind of see a similar phenomenon for interacting particle systems, and actually this is open for the ASEP, before this theorem, and the tools used to prove this theorem actually in consequence or sort of in parallel also proved the exact same statements. So sort of this bike range fluctuations result in this sort of 2-point function result for the ASEP. Okay. So that was how, sort of the first result proving a stationary fluctuation result, a stationary fluctuation distribution result. So a statement about exact statistics for the stationary asymmetric exclusion, asymmetric simple exclusion process. Okay, so I want to quickly describe just a few slides. I don't want to go too long. I only have probably 5 minutes left. Just telling you a few words behind how to show the limit shape proof, because as I mentioned before, the Stochastic Six-Vertex model, its generator is fairly nasty due to the sequential update. So I want to describe how a somewhat different argument that doesn't really use the generator can be used to show these hydrodynamic limit results. And the basic ideas were of this results. They go under the name of constructive Euler hydrodynamics, and they were sort of proposed originally by the works of Bahaduran, Jill, Ravi Shankar, and Sada back around 20 years ago. So again, let me just remind you of the setup. We have some stochastic six-vertex model in the upper half plane. It has some initial data that's converging to some psi, some profiled psi. We'll try to show that after I scale properly, that this height function, it converges to the entropy solution to some Burgers type PDE with the proper initial data. And we'll define H, this sort of little h, to be the partial, the x derivative of this solution. So you should view it as sort of the density profile for the vertical arrows. And then H is given by some measurable function, which is the entropy solution. If I just sort of take this PDE here and plug it in, you'll get that H satisfies is the entropy solution to this PDE over here. Partial Y of H is equal to partial X of phi of H. Okay, with some proper initial data that's given by the derivative of psi. Okay, so the book is based on basically characterizing solutions of this sort of the finite speed of propagation, so finite speed of discrepancies. The second is sort of a stability statement for the height function, and the third is that you pin it down on certain Riemann profiles. And you show that if you have these three functions, so if I have these three properties, I'll tell you exactly what they are in a moment. If you have any function H that satisfies these three properties, then it had better be the solution to the entropy solution to this PDE. And what you'll show is that these three properties approximately hold for the stochastic six-vertex model. And the gain of this sort of framework is that it does not require really you to use very much about the model's Markov generator. You can sort of achieve this through coupling arguments. Okay, so let me just tell you a few quick words on what these properties are in more detail. I'll tell you what their analogs are for the stochastic. So let's let L naught denote the set of compactly supported measurable functions, U from R to -1, 1. So you should view this as sort of a density profile. And for any T that's non-negative and U in this sort of set of functions, we'll define basically a semi-group operator, PT of U, which is PT of U of X, PT of U, which is equal to H of XT, where H is the entropy solution to this PD had before, with initial data given by U. So it's basically just the evolution of U under this PDE, this Burgers type PDE. Okay, so you can view P as this sort of semi-group operator on the set of functions. And there are three properties. The three properties I had before. The first is this finite speed of propagation or finite speed of discrepancies. what it says is that whenever there exists some sort of uniform constant nu, since the following holds, whenever u and v are functions that coincide on some interval ab, if I evolve according to the standard group operator q, then these two functions will continue to coincide on some slightly smaller interval, a plus nu t, b minus nu t. Okay, so that's one property. The second property is that it's some notion of height stability. So if I take two functions uv in this L0, and I'll define some metric delta. So the same, I'll define in a second. So the statement is that delta q of u, the delta distance between q of u and q of v is at most the sort of initial distance between delta distance between u and v. And this delta distance by definition is the distance is the maximum supremum distance between h. So the distance between f and g is the supremum distance between h of f and h of g, where h is sort of the integral of, it's kind of the antiderivative of f. So it's the integral from minus infinity to x of f. So you can view it as sort of the height function associated with the density, or the current associated with the density. So what this is basically saying is that if I have one height function that's within some delta of another height function, then if I evolve it, it's going to remain that case. That height function is going to be still within delta of that height function after any period of time. Okay, and the third is that they coincide with the original semigroup operator P on the Riemann profile. So if I have some u of x, which is rho to the left of 0 and lambda to the right of 0, then qt of u is equal to pt of u. So the fact is that, of course, that this operator P will satisfy these three properties. The third property is somewhat trivial. The first and the second take some work, but they're true. And the claim is that if Q satisfies these three properties, then it coincides with P. So this is a way of sort of characterizing a solution to this, the entropy solution to this PDE. So as above, this was sort of stated and proven in this work of Bahador and Jill, Ravi Shankar and Sada. But I mean, the idea behind this proof was largely due to ideas of Glim that dated back some 55 years ago. Okay, so now I just want to state what these three properties look like for the stochastic six-vertex model. So the first is that, okay, there's just a constant the finite speed of propagation statement is the following. So if I have two stochastic six-vertex models, E1 and E2, whose initial data coincides in some interval AB, then with some exponential probability, they'll also coincide on the slightly smaller interval, on the sort of rectangle, A plus nu t, B minus nu t, cross 0t. So they will coincide on the slightly smaller rectangle. And the proof is based by coupling arguments, sort of a finite speed of propagation, finite speed of discrepancies coming from coupling arguments. Okay, the second statement, again, this is sort of a height stability. It's the following. So if I take two stochastic six-vertex models, H1 and H2, that satisfy the property that their maximum difference is at most A, initially, their initial maximum distance is at most A, then with the following holds. Okay, and I have some function f, so that with high probability h1 of xt minus f is at least some b. Then with high probability, I'll have that h2 minus f is at most a plus b with high probability. So what this is basically saying, if you imagine b to be basically 0, this is basically saying that the distance between h1 and h2 is at most a for all time. So this is just some version of that where I introduce this additional parameter b. And this proof is again based on some sort of coupling argument. And the third statement is again the coincidence in the Riemann profile. So if I fix any some rho and lambda, then the limit shape result, I mean the sort of the theorem I had listed before, holds under double-sided rho lambda Bernoulli initial data. So it's some sort of approximation of the Riemann profile. So if rho is bigger than or equal to lambda, this is sort of corresponding to the existence of a rarefaction fan. And it's implied by exactly solvable. I mean, you can sort of solve the model exactly in work with myself and Alexei Borden back in 2016. And if rho is less than lambda, then this is sort of corresponding to a shock. And the exactly solvable tools, they're more difficult to adapt, and one instead adopts probabilistic ideas back due to Angel Veras and Liggett some number of decades ago. So this is sort of the schema proof of showing the limit shape, the hydrodynamic limit shape result for the stochastic six-vertex model. So I will just skip a few slides and conclude. So the summary is that we discussed various asymptotic behaviors for the stochastic six-vertex model under arbitrary initial data. It has a limit shape result given by the entropy solution to a certain PDE, and you can view this as a hydrodynamic limit shape result to the underlying interacting particle system. We showed a local statistics result. The local statistics are governed by pure states of the appropriate slope, and these pure states exhibit these KBZ fluctuations where I see t to the 1/3 fluctuations with Bike-Rain's distribution on a characteristic line. And everywhere off the characteristic line, you see Gaussian fluctuations. And we showed that sort of if you start the stochastic six-vertex model under arbitrary initial data, they'll converge to these pure states. And the proof of the limit shape result was based on a characterization of entropy solutions to a PDE that satisfied these three properties: finite speed with discrepancies, high stability, and coincidence on these Riemann profiles. And the game then is to show that these three properties hold. There's some sort of discrete analog for each of these three properties for the stochastic six-vertex model. So thank you for your time, and sorry for going over these technical problems. So.
Thank you very much, Amol, for this nice talk, very instructive. Is there any question or comments? Let's.
I have a question. No, I was just wondering if you, okay, you mentioned the color six-vertex model. I guess there is also a map to go from there to multi-species exclusion. And also if you can tune different your B1, B2 and rescaling, can you also get TASEP from the six-vertex?
Yes. So there are two questions here. So let me answer the second one first. I actually get ASEP, as I was saying, by the scaling. Okay. This is the set B1 and B2 very small, and send epsilon 0 and time to rescale time. So if you just let L equal 0, which is the equivalent to setting B1 equal to 0, but still scale this one, this double horizontal, you will get TASEP.
Okay. Okay. Yeah. So you just set L equal to 0. Yeah. Mm-hmm.
Your second
so
question.
It's the same.
I mean, you just set L equal to 0 basically.
Yeah. So it's the same.
But still keep your R and you'll get TASEP. Okay. Now you were asking about exactly the same. Yeah. Correct. Yeah. Okay. Now the second question you were asking was about these color systems. I didn't really define them. I mean, so basically, you can define a colored version of the stochastic six-vertex model, or a multi-species version of it, where each arrow comes with its own species, and these species can interact according to similar rules as we had before. Okay. So this will give you some colored version of the six-vertex model, and under the same rescaling, exactly the same rescaling, you'll get a multi-species ASAP. So it will converge to a multi-species ASAP under the same rescaling.
Okay. And
so there's
so
a
you
very
also have
direct
a
connection between the two. And
okay. So you also have a notion of, let's say, priority in the color six-vertex model, which is the class of the particles in the particle system.
Yeah. So okay, for example, here you can say, okay, so I have two colors. Exactly. So in this example here, I have maybe two classes. There's a red and a blue, Okay. And the red you should view as heavier than the blue. So maybe it has a smaller index. It's a top class, first class, blue, second class. Okay. And then this is telling you how the red and the blue interact when they meet each other. And as you can see, the red basically doesn't even see the blue, much like you see in the ASAP first class particle, it acts like it doesn't see the second class particle. Okay. So this is sort of how you might describe a multi-species six-vertex model or stochastic six-vertex model. And if you do the same scaling limit as before, it will literally converge to the multi-species ASAP.
Yeah, makes sense. Thanks.
Yeah.
Other question, Milton?
I see a question in the chat.
It's related to this multi-species.
I also see a question in the chat. Oh.
Oh, yeah, sorry. Go ahead and then I ask my question.
Okay.
Who is speaking?
Leandro. In the chat, no. So you can ask the question on the chat first, and then you can go with me.
You can go directly. Who is?
Okay. So is this model? I think there's a question in the chat. Or Milton can go. I mean, either one.
Okay. No, so it's related to this.
Maybe I can quickly answer the question in the chat. Okay.
No question. I don't see any question.
So okay. So I was thinking. So, do you have any I think probably is maybe just at the level of conjectures. When you have this multi-species or this color six-vertex model, how the height function looks like. I mean, does it satisfy a sort of systems of Borger's equation? How do we know about that problem?
Okay. Yes. So the limit shape will be basically a triviality coming from that. The hydrodynamic limit shape will be basically following from this hydrodynamic limit shape. The same way as if you take a two-species ASEP, the hydrodynamic limit shape of that model just comes directly from the hydrodynamic limit shape from the one-species ASEP by just subtracting. I take the limit shape for the first two particles together, and I take the limit shape for the goal, and then I subtract the crystals. This will give me a PDE for. I mean, this will give me a PDE for each of the particles individually. So from the level of limit, I mean, this is all fairly known. Now, on the level of fluctuations, this is much more subtle, and this has not really been looked into in great detail yet. There are works of so in certain, it makes you feel any better. This is irritating for me. If it makes you feel any better, this is equally irritating for me as it is for you. So yes, Milton, you were asking about the from the colored models, correct?
Yeah, exactly. So where do we stand for the scale limits for the colored model?
Right, hydrodynamics, you can read off from the hydrodynamics of the single species models. Yeah. And the reason for that is just the coupling. Okay. I mean, just look at the first two classes together in the first class, and this will give you the limit shape for each one, and each one holds with high probability, and therefore you get what you want. Now, the fluctuations are more subtle. Okay. And these have not been looked into in great detail as of yet. I mean, it's somewhat similar status as for the multi-species ASEP in the sense that not much has been done. I mean, you expect to see, I mean, there are these generalized fluctuating hydrodynamic predictions of Spohn and Mendel or Spohn, which predicts you should see certain KPZ modes in certain directions and Gaussian modes in others, only in very specific cases that are not quite given by the models that I discussed in my talk are these known.
Okay.
Yeah.
Yes,
Any other question? Leandro?
There is one in the chat.
Yeah.
Can you read it for me? Because when I disconnected,
I can read it for you. So Stella Bresasco, she's asking if this model is related to Ian diagrams of plane partitions of an integer.
So, okay, so, right. So, okay, so let me see how to best answer this. So there are dynamical models that you can get from looking at plane partitions. These are not the same as those. So I mean, there's a bulk class. I mean, there's a fairly wide class of subbable models that you can get from looking at, like stochastic subbable models that you can get from looking at plane partitions of integers, and these are somewhat different. I mean, these don't sort of fall into that class. That said, you can view these as sort of different dynamics on sets of partitions. Namely, if I look at the, I can try to share my screen again. If I look at the locations of where these, if I sort of fix a row, and I look at the locations of the up arrows, I can kind of partition from them, right? I mean, like this partition might be, for example, 1, 2, 4, 7, 9, or something like that. Okay, and then I can view this as sort of a dynamic on the partitions. You know, I evolve the partitions as I go from row to row, and you can view this as some sort of three-dimensional partition type thing. So it can kind of be viewed in that sense, but it doesn't follow. I mean, like there's a class of sort of subbable models that are fairly well known by this point that are determinantal that come from plane partitions, and this does not fall into those classes. So I hope I answered your question. Please let me know.
Yeah.
Okay, yeah.
Any other question?
So may I ask another question, or is it a little bit too much? Okay, Leandro, go ahead, Leandro.
Okay, thank you Thank you, Amol, for your nice talk. And so I want to talk about this. I want to ask you something about this 2-point function.
Yeah.
So can you? So this should also converge to this second derivative of the variance of the Bike rates. So can you also show this, or in your is this contained in your result? And so another question is, you can prove this.
So as you know, wait, but let me answer that one. Oh, or go ahead.
Okay. So you can relate this 2-point functions with some
what
sort
I was saying.
It's cutting.
Yeah.
Amol, you understood the question?
Correctly. I think can you please ask it again, Leandro? I'm having a little trouble.
Okay, so the first question is if you can get the limit in some sort of weak sense of this 2-point function to the second derivative of the variance of the Bake range distribution, and also if you prove this kind of result by the one that is described in your slide, for instance, that the covariance, the 2-point function of u and v scaled as u minus v to the power minus 2/3, by relating this 2-point function with some sort of second class particle or something like that.
Okay. Yeah. So the first statement is that this is not actually in the paper. So I mean, but there is a relation, much like for the ASYMP, which you know well. There is a relation between the variance of the current and the 2-point function. It's something, as you just mentioned, it's something like the Laplacian of the variance is going to give you the 2-point function. That will also hold here. I mean, in the Six Vertex model, the same will be the same. Now, as you know, so hopefully that answers your second question. Now, your first question, to actually prove the statement, you would need something about the tail. I mean, you would need some sort of sharp enough decay on the tail of the of this distribution. In order to say that the variance of this thing converges to the variance of the Bike grains. Now, such a statement is in the realm of technology. I mean, there are tools that would allow such a proof, although it's not in the literature yet.
Okay.
Yeah. So hopefully I've answered your question. Or yeah.
Okay. Thank you.
Yeah, my pleasure.
Milton.
Oh yes, yeah. So. Now, have people consider the Glauber dynamics for this 6-vector measures? I mean, now I'm thinking about it as if like in the easy model, now where you put Glauber dynamics, and that's something people have been studying, like mixing properties, etc. So. Is there something about that for the 6-vector model? Do you know?
You're asked. This is a good question, and so let me tell you what the predictions are and what's proven. Okay. So let me go back. I can actually say this for. Just let me know if my internet is bad. I'm getting paranoid about this. But yeah. So I'll try to tell you what's known and what's predicted. Okay, so there are 6 weights. Okay, and they depend. So the qualitative properties of mix should depend on a single parameter dependent on these 6 weights. It's called delta. So this delta is equal to A1, A2. I mean, there's a formula for it in terms of these weights. Okay, it's like A1, A2 plus B1, B2 minus C1, C2 over 2 times the square root of A1, A2, B1, B2. This is some explicit number. Okay. So depending on the value of delta, you expect different mixing properties. Okay, so if delta is between -1 and 1, you expect this model to mix in quadratic time. So it should mix polynomial fast, in particular quadratic time, according actually to mean curvature flow. So this is somewhat, so in terms of dimer models, it's shown by, say, I think Tonanelli and Laslier, that if you take a dimer model, then this thing will mix in quadratic time. You expect to see the same thing for the six-vertex model when the delta is between -1 and 1. Okay, now if delta is bigger than 1, which is actually the regime of this model, of this stochastic model. So if you compute the delta here, you'll see that delta is bigger than 1. And so in this situation, you expect to see slow mixing. Okay, exponentially slow mixing. However, if you fix the boundary conditions properly, there are certain choices of boundary conditions for you, which you actually expect to see fast mixing. So this is again somewhat analogous to the Ising model. The Ising model on a torus at low temperature, it will mix very slowly. But if you take the Ising model on a rectangle conditions, then you expect it to actually mix quickly. So a fairly similar phenomenon is expected to occur in the stochastic six-vertex model. And likewise, if I take delta less than -1, this is known as the anti-Ferroelectrics, you again expect to see a similar phenomenon where at if I take the stochastic six-vertex model on torus or on fairly bad boundary conditions, whatever that means, it will mix slowly. But if I tune the boundary conditions, these are the predictions. I have this sort of critical phase in which I expect to see fast mixing and polynomial mixing everywhere. And in these sort of two extreme phases, one of which includes the stochastic six-vertex model, you expect to see slow mixing, except if the boundary conditions are tuned correctly, where you expect to see fast mixing. Okay, so that's sort of the landscape of predictions. Okay, so now in terms of proof, not much of this has really been proven. So I mean, so I think in this delta between -1 and 1, if delta's at 0 or like sort of close-ish to 0, it's known. And delta's in sort of, there are sorts of slow mixing results in parts of the other two regimes. I can give you a more detailed description maybe later, but I mean, through email if you want. But it's the picture. I mean, you have partial results that are picking up proving parts of predictions and incomplete parts of these regimes.
Okay. Okay. Thank you.
Did I answer your question? I can go into more detail if you want, but
no, it's okay. I think
yeah.
I already took too much time from the questions.
I'm happy to answer them. I have a last question. Is any other question in the audience? Let me ask you a question. I am interested in this way that you propose to prove that invariance, that the proposed invariant measures are really invariant. That you say, I have two operators, and if you commute, if these operators commute, then and one of them applied to the empty configuration gives you the product measure, then the product measure is invariant.
Right.
For the six-vertex model.
Yeah.
You already told me that here, and I thought I was looking for an operator for the exclusion, or for the multi-class exclusion, that has the same property that you have for the Six-Vertex model. Would you have any idea of that? What it
yes.
would be?
So yeah. So you have to. I don't know how to guess these. You actually have to come up with them, and the way you come up with them is through this fusion procedure. Okay, it's by taking these six-vertex models and taking like a composition of these six-vertex models, specialized in a proper way, and if you sort of analytically continue, you'll get one of these. You'll get an arrow that looks like this. So if you do that, this does work in multi-species. So I will it will look something like this. I mean, the arrow will look something like this, except it will have, I mean, it will have probabilities for each measure. It will have probabilities for each if I have multiple particles, it will take that into account. So the reference maybe, okay. So unfortunately, this has not been written down in the literature yet, but the closest reference, which is somewhat similar, I will try to put it in the chat. Hold on. Okay, it's just give me 1 second to put it in the chat. So okay, maybe I'll just give you the title. So it's called Colored Vertex Models and Their Spectral Theory. So they look at these colored vertex models in very high detail, and one of their vertex configurations looks something like this. Put it in the chat.
I missed the authors.
Give me a second. Let me just put it in the chat. It'll be easier that way. By Borden and Wheeler. So I put hopefully I put it in the chat and you can see it. So this will have a very wide family of vertex weights that all will satisfy these commutational relations. And now if you specialize the parameters correctly, you will get you will get sort of these thick arrows that commute that will satisfy similar commutation properties. So did I answer your question, Pablo?
Yes, yes.
For now,
Thank
yeah,
you.
okay. Yeah, my pleasure.
Okay, I think that we can thank the speaker again.
Yeah, and I'm so sorry for these technical difficulties. I mean,
Yeah, no problem. It was a great talk. Thank you very much.
yeah.
Thank you very
Thanks,
much.
Amol.
Yeah.